Hello and welcome to your pre-practical lecture for your third experiment, the synthesis, characterization and reactivity of ferrocene. So essentially, let's start the conversation on what is ferrocene. Now, ferrocene is a compound with a molecular structure or a line structure that looks like this. And that is why it's called a sandwich structure, because it's an ion center which is sandwiched between two cyclopentadiene rings. And then, well, it looks like a sandwich, exactly how you would build a sandwich. And it's actually the compound for which Fisher and Wilkinson won the Nobel Prize for in 1973. And it opened up a whole new field of organometallic chemistry, or a field known as organometallic chemistry. And this organometallic chemistry is a field which studies then metal-carbon formal bonds, and formal bonds meaning bonds that have significant covalent character where a metal center is bonded physically to a carbon atom. As you can see in this 3D structure more clearly, the carbons are bonded to the metal center, better indicated than what it is here in the line structure. And that is where our compound comes from. Ferrocene also obeys the 18 electron rule configuration, so further indicating that it is a stable bond configuration and indeed is a molecular structure as we know it. Some uses that it has, there's a lot of research that is done on ferrocene. There's some industrial applications like anti-knocking agents in your petrol, and then even some pharmaceutical like anti-malarial and anti-cancer applications that it has. So building on the idea of ferrocene, so ferrocene can readily be reactive because these rings are actually quite aromatic. So in other words, you can have electrophilic aromatic substitution reactions on these carbons, so on the ring. And that's exactly something we will look at in our experiment, or in experiment 3, is to have such a reaction, to have a substitution reaction somewhere on the ring to form an acetylation of sorts on the ring. So we will acetylate our ferrocene. So we'll first make ferrocene and then we'll acetylate one of the rings of the ferrocene. Going on further, you might ask why we draw ferrocene in a specific manner. So we have that the one side of our cyclopentadiene ring is pointing forwards and the other part is pointing to the back. And this is, if you look, say, in other words, if you look at like that, you would see a conformation as such is called staggered. But you can also, in principle, get one that is eclipsed. But the eclipse for conformation is, of course, sterically not favored and energetically less favored as well. So usually you'll encounter the staggered formation, conformation more regularly, just because of steric reasons. So when you're drawing it, this is how you will draw it. Draw it with the one side of the ring pointing forward and the other side of the ring pointing backward, and the same for your acetylated product. Okay, so that's a general idea of the molecular structure of ferrocene and where ferrocene comes from in general. In terms of the bonding of ferrocene, so let's look at we will look at the molecular orbital diagram of ferrocene, the big molecular orbital diagram. But to start with that, we first need to make our bonding orbitals. And we'll start with the ligand orbitals for that. And we'll use the cyclopentadiene molecular orbitals to form the ligand orbitals. And here we'll only look at the pi orbitals. So in other words, the p orbitals that form the double bonds in our cyclopentadiene rings. That will constitute the molecular orbitals, so the highest energy orbitals available for bonding from the cyclopentadiene. So those that will provide electron density to the ion center to bond, essentially. That's all you need to take from this. And there are 5 of their options. with which there are two ones that have some symmetry. The first is one that has no nodal surface. The second has one nodal surface. So if you imagine a plane that goes up, let's go up and down. So from downwards goes upwards to there, and this one goes up and down like that. So it's almost sinusoidal curves going up and down like that. Essentially, those are the higher energy terms, lower energy terms, things that you would do in CMY 382. But for now, if you take it that we have 5 ligand orbitals, molecular orbitals that can bond with the iron core, that's perfectly fine for the purposes. And of course, this means that because there are 2 cyclopentadiene rings, that means there are then double that amount of ligand orbitals that can bond in the molecular orbital diagram. This, of course, then overlaps with our metal orbitals. So metal, the iron center has a 4s, a 3d z squared, a 3d xz, a 3d yz, a 3d x squared y squared, as well as a 4pz, a 4px, and a 4py, and then a 3d xy option. And all of these can overlap to form the complete molecular orbital diagram. The complete molecular orbital diagram, very intense diagram, I do get it, but if all this, what you take from it is that we fill 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 electrons, and we have our HOMO and we have our LUMO orbitals identified. It's perfectly fine. And that ferrocene obeys the 18 electron rule, and it can bond, and it is a formal carbon metal bond. That is why it's a field of organic organometallics. And I'm happy with what you've taken from these slides, because this is quite complex and nothing that you will really be able to analyze yet. But that's what we wanted to show you. Just some general idea of how the bonding of ferrocene works for now. Okay. Next, we will look now at the preparation of ferrocene and get into the more practical stuff. Now that we've established what it is, how it bonds, and the fact that it actually indeed exists. Okay, so the first step in your synthesis of ferrocene is to isolate your ligand, or your ligand in principle, your CP or your cyclopentadiene. So to do this, we get cyclopentadiene in its dimer form. So we get dicyclopentadiene, and we need to crack this before we have pure only cyclopentadiene. To do this, we will use distillation, and luckily bis-cyclopentadiene boils at 170 degrees and cyclopentadiene boils at 42 degrees. So these two are easily separated using a distillation method. So if we have a heated setup somewhere between these two temperatures, we will have a separation of these two products. So hence, in this flask, you have a mixture of these two in equilibrium. And if you start removing this one, of course, by Le Chatelier's process or principle, you will have a shift in equilibrium where this continually shifts and produces this. And then we remove this product to the distillate, which we keep below 25 degrees Celsius to ensure that we don't have dimerization back to the bis product. And then we can, where you will collect your CP for the start of your reaction. You won't actually do this on your own. This will be performed for you. However, it's important for you to know that this is actually something that happens. So essentially, this is where it comes from. Okay. Once you've isolated your CP, of course, we need actually CP minus. So in other words, we are going to deprotonate it in dimethoxyethane. So using potassium hydroxide, which of course is a base, you will deprotonate your CP to form CP minus. And then once you have Cp minus, you will add your ferrous chloride in DMSO, and that will then form your ferrocene. And you will do this under what we call inert conditions, which is something you might not have come across, or you might have come across. So we'll discuss that next. So inert conditions essentially mean that in air we have reactants, so meaning oxygen and moisture, which can react with our product or reagents, which can then neutralize them from reacting in the certain way that we would like, or destroy our product which we have formed. So to minimize this, we usually use argon, but argon is quite expensive. So in your case, you'll be using nitrogen. But the principle is, because argon is much heavier than air, its density is much higher than air, or than the mixture of what air consists of. Once you let argon into the system, argon will lie below any air, and then your reaction mixture is covered with a layer of argon. And of course, argon is inert, nitrogen is also inert. It's something that will not react with anything else. So in other words, your reaction mixture is allowed to react with only that what you place inside the reaction mixture itself. That's the principle of inert conditions. When we use nitrogen, you are going to continuously purge your system, and you will have like a little balloon system that we put up. So you'll collect nitrogen, purge your system, and then collect nitrogen again, allow nitrogen to be added to the system, continuous flow throughout the system. So every time you add nitrogen, you're going to open this stopper, add some nitrogen, push out all the air that is in there to try and only have nitrogen in the top part of these flasks to create an inert atmosphere on top of your reagent mixture in here, so that you can only have your reagents reacting with themselves instead of reacting with any moisture or oxygen left in your flask. And that's the principle behind your inert conditions. Okay, you will do so. That's important for the steps where you have your Cp minus or your Cp reacting with your potassium hydroxide, as well as once you add your ferrous chloride. Or essentially once you add your ferrous chloride, that's important for that step. So only after the deprotonation, but you can start it beforehand. The acetylation of ferrocene is of course an electrophilic aromatic substitution reaction. As we've mentioned before, ferrocene will easily undergo these types of reactions. So the Cp ring will be easily acetylated, but we cannot really control how it is acetylated. So bis acetylation can easily occur. So you can have an acetylation of your ferrocene here, but it can also acetylate on this ring and this ring, because these rings are symmetrical and identical. So that is what is included in the byproduct. So you can have this product forming as well as some byproducts where both of these Cp rings are acetylated. And in our case, we use a Lewis catalyst, a Lewis acid catalyst, which is phosphoric acid, H3PO4, and then we will separate all our byproducts as well as any unacetyl or acetyl apologies, any of your acetic acid which has not reacted, which is left in the system, as well as any ferrocene which has also not been converted to acetyl, monoacetyl ferrocene in your system. So that is what we'll look. But first we'll look at the mechanism of how your Cp ring is acetylated. Essentially, your acetylation is going to occur via a so-called Field-Crafts acetylation mechanism. And in this, your acetic anhydride is first protonated, where this occurs, and then it splits into acetic acid and then an psyllium ion, which is your electrophile, which will then attack your nucleophile, which is your CP ring on your ferrocene. Okay, and then we will have a base workup where you remove a proton. So in your ferrocene, you will then have your reaction as follows, and finally you'll have your acetylated product. I don't want to go into too much detail because you sort of have to use this to answer some of your questions in your assignment. But this is the broad overview, and you can use this to guide your answers. Okay. Next, once you've acetylated your product, and you've also have the bis-acetylated product, and of course you also have some starting reagent, which is going to be ferrocene in your reaction mixture, then you're going to have to purify this, and you will do this via column chromatography, which I hope by now you identified as the main method of separation. And in this experiment, it's different from your second experiment in that we will use polarity and solubility in solvents rather than the ion exchange properties of our reagents. So meaning we will use two different solvents to extract our different products rather than using the same eluent. So in experiment 2, we use sodium chloride, and here we're going to use use ether and then hexane. Okay, but let's first talk about why. So ferrocene has no net dipole. As you can see, there's no group anywhere attached, anywhere that produces any dipole on it. Acetylated ferrocene has a dipole because of this acetyl group. So in other words, it has some sort of dipole moment pointing towards that. So in your column, once you've packed your column, of course, again, you use cotton wool, you use silica, you'll have your ground up dry mixture. So you'll ground up whatever the product was, your crude product you got from your acetylated mixture, you put that in there, and you put some sand, and then you'll use different solvents to collect either the pure or the non-polar and the polar products from your column, okay, which we'll get into now. We will first remove the non-polar product with hexane. So in other words, if you think about it, the non-polar product, which one would that be? Probably the one with no dipole. Then you remove the polar product using diethyl ether. So that will be the one with some sort of dipole. So, which product will come out first? Ask, use your chemistry knowledge, compare with your starting material, but you also need to characterize your fractions you collect from this column using UV-Vis, IR, NMR to confirm your prediction that we've made here. So we expect our column to behave as such. So in other words, with hexane to remove your pure ferrocene, and your diethyl ether to remove your acetylated ferrocene, which is red. Your ferrocene is this orange color, and your acetylated ferrocene is red. This is what we expect, and of course then you always use your spectra to confirm these expectations, right? In terms of characterization, to further focus on that, you're going to determine melting points. You will determine that for crude ferrocene, your purified ferrocene, but you did through the sublimation, and your purified acetyl ferrocene, which you collected after the column, which is essentially your diethyl ether fraction. Then you're going to compare that with literature values, which you'll get from Reaxys or whatever you would like to use to get those literature values. We'll also provide you with FTIR spectra. You'll measure this for ferrocene and purified acetyl ferrocene, where you'll just compare the key frequencies which alludes to specific functional groups. In other words, what is the differences between these two once again? So to ensure that acetylation occurred, essentially, and then UV-Vis, see what is the differences between your purified acetyl ferrocene and your acetylated ferrocene. once again, just comparing your primary absorption bands and then correlating it with the color, so orange and red. We also provide you with proton NMR, which is measured for purified ferrocene and purified acetylferrocene. You will look at these are very well identified already for you. You just need to sort of discuss them. Correlating any differences in the structures and the functional groups present. In other words, once again, the effects of the different functional groups, and then just, as I said, the effects of those different, the acetylation step. Finally, just a quick recap. We want to synthesize ferrocene, evaluate its reactivity. So in other words, synthesizing acetylferrocene. Then we're going to purify our crude acetylferrocene using a chromatographic method. And then we're going to fully characterize them using FTIR, using UV-Vis, using proton NMR. You will have 3 weeks to complete this experiment. So you will take your time to go through all these steps to ensure that you have enough time to answer all your questions. And please ask questions. That is the most important thing that I can emphasize. Please ask questions while you're going through this process. And of course, you're going to write a full report answering these questions at the end of your 3 weeks. Okay, so as always, good luck and thank you for watching.